Let us first start by examining the shapes of the atomic orbitals for carbon. The 2s atomic orbital is a sphere, and the three 2p atomic orbitals are shaped like dumbbells, oriented along the three axes 2px, 2py, and 2pz. Think of these four atomic orbitals as three-dimensional shapes, where you are most likely to find an electron 90% of the time. Notice that the electrons have access to both lobes for the 2p orbitals. Starting from the abbreviated electron configuration for carbon, one can imagine promoting an electron from the 2s atomic orbital to the unoccupied 2pz atomic orbital. Although we now have four unpaired electrons for bonding, we still can't explain the experimentally observed bond angles for a tetravalent carbon. Thus, when we mix the 2s atomic orbital with all three 2p atomic orbitals, we create four new degenerate energy hybrid orbitals. The shape of the new sp3 hybrid orbital is best characterized as 1 part s and 3 parts p. As with all orbitals, think of these hybrid orbitals as three-dimensional shapes, where you can find the electron 90% of the time. The hybridized carbon now possesses four unpaired valence electrons and is said to be an sp3 hybridized carbon. When we superimpose all four sp3 hybrid orbitals onto the carbon atom, it becomes quite cumbersome and confusing. Thus, we simply show how the electrons in the hybrid orbitals are oriented in three dimensions. The four new hybrid orbitals attempt to get as far apart from each other as possible, 109.5 degrees. Think of this as the orbitals attempting to minimize repulsions between them. Thus, they are oriented towards the corners of a tetrahedron with all angles at 109.